Using a pipette, transfer the solvent used to prepare the solutions and the two solutions into cuvettes that are clean, dry, and scratch-free, ensuring that the meniscus rests perfectly on the fill line. When analyzing a colored solution, ensure that you scan across all wavelengths. In this specific experiment, the appropriate range is 200 to 800 nanometers. The reason we do this is that different compounds will absorb light differently across the spectrum, and scanning across all wavelengths helps us to identify at what wavelength the substance will absorb the most light. Secondly, this is to aid in detecting impurities or multiple absorbing species in the solution. Samples won't always be pure. Reagents can break down, contaminants can make their way into it, or some of its other components absorb light as well. Measuring at a single wavelength can lead to inaccurate concentration calculations if the selected wavelength overlaps multiple species' absorption bands. After confirming that the spectrophotometer is zeroed and set to scan the 200 to 800 nanometer range, gently and thoroughly wipe all sides of the cuvette, and gently place the cuvette in the machine with the clean sides and the light beam. Close the lid of the machine and scan the absorbance of the sample. Record the absorbance of the sample in your notebook. Then carefully open the door, remove the cuvette from the machine, and close the lid back. Repeat this procedure with all samples. Once we have collected the absorption data from the full scan, we can identify the lambda max, the wavelength where the solution absorbs the maximum amount of light, the highest peak on an absorbance versus wavelength graph. We can connect all of this to the Beer-Lambert law as shown. A is the absorbance value measured by the spectrophotometer. This value is read directly from the machine. The epsilon is indicative of molar absorptivity, which can be determined by finding the slope of the line that forms from graphing the collected data points. B is the path length, or distance the light travels through the sample. For a standard cuvette, B equals 1 centimeter. C is the concentration, or the amount of the absorbing species in the solution. This can be calculated using a calibration curve or by rearranging this equation after measuring absorbance. According to the Beer-Lambert law, absorbance and concentration have a linear relationship. In other words, as concentration increases, absorbance will also increase in a linear pattern and vice versa, so long as the machine and graph setup is done correctly. A crucial part of this setup is carefully wiping every cuvette clean of fingerprints and zeroing the machine. We do this using a cuvette filled with the same solvent as was used to prepare the solutions. Failure to properly clean the cuvettes and zero the machine will lead to the machine including the solvent's absorbance, fingerprints, or any other disturbance in the measurement. And if this happens, your reading will turn out higher than they should be, leading to incorrect high concentration calculations. Be sure to shut down the machine area and clean up your group's lab space. Dispose of all waste in the designated waste containers, and clean the cuvettes using soap. Rinse with water, thoroughly dry each piece, and put away each piece in its designated storage area.